Hi, this is Emmanuel. Welcome. This video has two phases. The first phase, I'll use slides to explain why you need to study algorithms, problems solved by algorithms, and the three most important restraints to consider when implementing an algorithm. The final phase, I'll pick two sorting algorithms, merge sort and insertion sort. I'll analyze their time complexities and we will pick the best among the two. So, without wasting your time, let's dive in. This will be a short presentation to explain why you need to study algorithms. So, what is an algorithm? They are like well-defined computational procedure that takes inputs and produces outputs. Key terms to pick it up: inputs and outputs, and computational. So this explains that humans, we can produce algorithms using our brain. We don't really necessarily have to depend on the computer to produce an algorithm. Example can be multiplying two integers, dividing multiple integers, and so forth. But the problem is the complexity of an algorithm. The more complicated it becomes, the easier humans are going to make errors, because humans, we are prone to errors. We are bound to make mistakes. Computers, on the other hand, can produce a high optimized algorithms more efficiently than humans. So that is why most or almost all our algorithms are being computational, using computational procedure. So we humans will feed in the inputs and the computer will process it and brings back the output for us. A clear example is we should sort sequence of numbers into non-decreasing order. We have an input A1, A2 up to AN, and the output is going to be A1 should be less than or equals to A2, and that should be less than or equals to the next number up to AN. If we have these integer values 31, 41, 59, 26, 41, and 58, what do you think is going to be the output? Just take a moment and write it down. The answer is going to be, the computer is going to look through this, pick the smallest number, which is 26. So 26 will be the first number. Look through it again. What is the second smallest? That is 31. So 26, 31. The smallest will be 41, 41. That will come next. Then 58, and the last index is going to be 59. And that is how they are going to be sorted. So, what is our goal? Our main goal is to create or implement an algorithm that works correctly. So the algorithm that we are going to use, when we feed in this input, it should bring back the output that we just talked about. So it should work correctly. On the other hand, we don't want an algorithm that does not work. So before you consider anything about an algorithm, you have to think about how correctly is this algorithm. Is this algorithm correct? That is the most important thing. Most of us think about writing or implementing an algorithm by making it more optimized, making it more cost efficient, and the rest, without technically considering how correct the algorithm is going to be. But that should be your key priority first before you think about the rest. It has to be consistent. And what do we mean by a consistent algorithm? A consistent algorithm does not matter the size of the inputs. It's still going to yield the correct output. On the other hand, the algorithm is not only going to consider sorting this 6 or this length of inputs. Even if you provide millions of inputs, it should be able to provide a correct output. And the last part should be cost efficient, and I'll dive more into the cost efficiency later. But basically, the cost efficient is the time the algorithm is going to take the algorithm to produce the output, so it should be fast and optimized. Let's look at some problems that have been solved by algorithms. I'm going to talk about internet used to retrieve large amounts of information. Let's talk about Google search engines. Provided you go to Google and you type in, you want to find any information about a data, considerably you will see a list of populated outputs that comes from your search, and Google use algorithms to be able to sort all those outputs so it could meet your requirements, so you could be satisfied. The next example we're going to talk about is e-commerce enables goods and services to be negotiated and exchanged electronically. Clear example is Amazon. Users could use Amazon to buy products, and those products could be shipped to them within some few days. They will get their products. Those products in the catalogs uses algorithms to sort those products. That is why when you type computers will be populated, a list of computers, ordered by their brand, by their name, by their model, and by their specs. All these are algorithms that are used on those sites. Finding the shortest path between multiple routes. Considering you are at point A and you want to go to your final destination, which is D, either you pass through A, C, D, or you pass through A, B, D, or you go through A, B, C, D, or you go through A to D. They are all routes that can take you to your destination. We have an algorithm that will consider all these options and will pick the shortest option that is the shortest route that will take you to your destination. In the long term, that means you are going to pretty much save time. The last problem that I'm going to spend a little time on will be the Human Genome Project. We are going to read a little bit about the Human Genome Project from Wikipedia. It is a scientific research project with the goal of determining the base pairs that make up human DNA and of identifying and mapping all of the genes of the human genome from both physical and functional standpoint. So it's basically the grouping of DNAs, right? And with this project, using algorithms, scientists were able to categorically sort thousands of DNAs. So that is really cool to know. Constraints. This will be the last thing to consider. Our goal is to solve the problem not only correctly but also efficiently. 3 things we are going to consider are time, memory, and space. That is going to be the talk around every algorithm we picked up. We are going to analyze the algorithm, the time complexity. We are going to talk about the space complexity and also the memory. So time is the most important as it keeps marching onwards. And the memory is important when working with large data sets. If you have extremely large data sets, it could lead to overflows. So you want to consider your memory, so like you can be able to handle every input case. The space is important when working on legacy systems with little space, that is, old applications. Modern applications, space is not a problem because space has become cheap of late. But when you are working on legacy applications, legacy systems, you have to think about space. Our measure of efficiency will be focused on speed, which is how long an algorithm takes to produce its results. So that will be our main point. What's next? We are going to pick two sorting algorithms. We will pick insertion sort and merge sort. We will implement the algorithm. We will look at the mathematical proof of the algorithm. We talk about the time complexity between the two. Then we will pick the best among the two using the time complexities. Let's talk about insertion sort. So insertion sort is where you have this given input 8, 7, 3, 4, 2, and you are going to have a left side and a right side, and you are going to keep inserting from this side and you keep going. So 2 will come, then 3 will come, 4 will come, 7 will come, then 8 will come. So then at the end, then you have your insertion sort. The algorithm for the insertion sort is pretty much straightforward. So insertion, you have your array that will be given to you. Then you just loop over it, which is I1. You start from 1, then I is less than or equals to num.length minus 1 I plus plus. So you have an integer of key, which is num at I, and you have integer of j, which is I minus 1. Then while j is greater than or equals to 0 and num at j is greater than key, then we come into there. Then we assign num at j plus 1 to num at j. Then we reduce j. Afterwards we come num at j plus 1 equals to key. Then so this is the algorithm for the insertion. So we are going to go through and use this example to go through. So we first start where I is equals to 1, j will be equals to 0. Then we come to the while loop. We check j is 0. So it's equals to 0. We come to the next condition, num at j, which is equals to 8, is greater than 7. So 8 and 7, 8 is greater than 7. So this is j for now, and it's 0, right? Index at 0, 1, 2, 3, and 4. In the 0, 1, 2, 3, and 4. Then we come here to the while, the block statement within the while, num j plus 1, which is j is 0, so j plus 1 is 1. J is equals to 1. Then we assign num at j. Num at j was 8, so we assign 8 here. So it's going to overwrite the 7. Then we reduce j. So j is already 0. If you reduce it by 1, it's going to be -1. We come to the while statement, we check is j, which is -1, this will terminate because it's not equals to 0 or it's not greater than 0. Then we jump here to this statement, num at j plus 1 equals to key. So j is already -1 plus 1, that means j is equals to 0. Where is j0? j0 is here and 8 is there. So we overwrite it with key, and key is num at I, and I is 1 because we already set I to 1, and I1 was 7. So we store I before we overwrite it, right? So we set 7 to 8, so it's going to overwrite it, so 7 will come here. So after the first iteration, we are going to have 7, 8, 3, 3. So after second iteration, I is going to be 2, j, and the key is going to be 0, 1, 2. So the key is going to be 3, and j is going to be I minus 1, which is 2 minus 1, 2 minus 1, which is equal to 1. So j is 1. Is greater than 0. Num at 1, which is 8 in this case, is greater than key. So we are going to overwrite it. Num at j plus 1, which is 1 plus 1, which is 2. So num at 2 is going to be num at j, and num at j is 8. So where we have the 3, we will put 8 there, and it's going to overwrite that 3. But we already know like 3 has been stored into the key, right? So then we reduce this by 1. By reducing it by 1, it was already 1, so we reduce it by 1, then it is going to be equals to 0. So j is equals to 0 now. Then we go to the while statement, then we check is j greater than or equal to 0. Yes, it's equal to 0. Is this num at j greater than key? Yes. So num at j, which is 0, is 7, right? And 7 is greater than key, which is 3. We come here, we check num at j plus 1. We are going to assign the value at num at j, which is 7, to num at j plus 1. So that means num at j plus 1 is num at 1, which is index 1. Then we put in 7, right? And we have 8 here. So we come back, we reduce j again. J is 0, so we reduce it. J is going to be -1. We check and the loop terminates. We come here, j is already -1 plus 1 equals to 0. So then we know our key is 3. So j num at 0, we put 3 there. So 3 will come here, right? So we have 3, 7, 8. Then we increment I again. So I is going to be 3, which is num at the key is going to be 4. When the key is 4, that means j is supposed to be 3 minus 1, and that is going to be 2. So we come here, this pass, num at 2 is 8. 8 is greater than the key because it's 4. So then we set 8 here, right? Continuous 7 will be set here to override the 8. And when it gets here, it will fail because num at j, which will be 3, is less than the key. So then you overwrite the 4 with the 7 with the 4, and 8 will be here. Right? So then we increment I is 4, index 4, which is 2, and we will do the same. 8 will overwrite it, 7 will overwrite 8, 4 will overwrite 7, 3 will overwrite 4, then the final we put our 2 here, and we get our sorted array. That is how insertion sort performs its operation. We have the cost and we have the time, and we are going to add this up. We will get the worst case. The worst case is going to be a n squared plus bn plus c. We don't really care about the coefficient, so it's going to be n squared plus n. We take all the coefficients out, and we don't, considering this, we will take the biggest one. So worst case is going to be n squared. So the worst case of insertion sort, worst and average case, they are going to be n squared. The best case is going to be n, which is linear time. So that is what we have for the insertion sorts. That is the time complexity, how fast it's going to take for this algorithm to sort n number of inputs. So we are going to analyze merge sorts and compare it to the insertion sorts, and after that we will decide which algorithm to go after. So I can write the algorithm for merge sort, considering if you have this array, right? Merge sort is you call merge sort like private void sorts, where you have the array, which is num, and you get an integer of L and of R, which technically L and R, L is in the 0 and R is 0, 1, 2, 3, 4, 5, 6, 7, the last index. So once you come here, you have to find the midpoint of this array, and that is, you add the left and the R, which is 0 plus the last index, then you divide by 2, then you get the midpoint. So you are going to keep recursively call this sort until you get to the last, you get to the situation where you cannot literally find the midpoint again. So that is what we are going to do. So you call the sort, then so once we divide this, we get this 3.5, which we get like this pieces. So this piece and that piece. Then we come here, then we divide this piece. Then we get this piece, then that piece. Then we come here, then we divide this piece, then we get this piece and that piece. Then we come here, then we divide, then we get this piece and that piece. Then after that, we merge sort them. So this is what we're going to do. We pass in recursively, we pass in this and L and M, which is the median, because this is the ending. Then we recursively call the other half to nums, which is the lowest is n plus 1. Then we call the R. So after that, then we are going to merge sort everything, right? So we pass in the nums, which is the array that we've literally divided into chunks. Then we pass in the medium L and right. right? So this is what we will get. So now I'm going to clean this first part because we are going to code this, or if there is space, I think I can code it here. Let's see if it can go there. So then we have private void merge sort, pretty much. So we will have the array nums, int medium, int left, and int right, all here. So first thing that we are going to consider doing is we are going to create an array, which is L. This one we are going to have a new int, and this is going to be equals to m minus L plus 1. Then we do the same for the R, which is the right. So we have two arrays, and this is going to take the n2. So then we are just going to copy the arrays into left and right, where we can just have like for int I equals to 0, I is less than n1, I plus plus, then li is equals to nums at L plus I. Then we close it. Then we do the same thing for the other array, which is this is going to be J. Let's represent here by J, right? J is less than n2, J plus plus, then R J is equals to nums at m plus 1 plus J. So we have our left and right. That is the left side array, we have the right side array. Now we are going to concatenate them and merge them. So we have our int k equals to L, and we have I0 J0, right? So while I is less than n1 and J is less than n2, then we come here, then we check if Li is less than or equals to Rj, that means we put it in front, right? And that is going to be nums at k, because k is going to be the lowest here. Then we put it there, and this is going to be Li. Else nums at k is going to be equals to Rj. So we satisfied it. After we do that, there is a probability that we will not fully satisfy the condition, because most of the arrays, considering if this list is 6 and this is 3, this will finish and there will be extra here. So we will satisfy that condition, and that is like while I is less than this, then we just here we increment it, and here, so after we concatenate it, we increment I plus plus, and here J plus plus 2. So here, then we just nums at k go to L at I plus plus k++. And we do the same thing for the other half, which is j less than n2 nums at k r at j. So k++, j++. So this is the algorithm, right? So it picks this, basically it picks that, and what it's going to do is split it. So you split it to here 2, 4, 5, 7. Then here to 1, 2, 3, 6, 2, 5, 4, 7, 5, 2, 4, 7. It does this 1, 3, 2, 6, 1, 3, 2, 6, and that is how it goes. So the time complexity for worst case, average case, and best case is going to be n log n. So we have to compare n log n for this merge sort algorithm to the worst case of insertion sort, which is n squared. Comparison of the two, it is clear that merge sort has the best time complexity, and that is how we can determine an efficient algorithm by analyzing the time complexity. In future videos, I will literally go step by step to analyze each step of this algorithm, but because of time's sake, I'm going to leave it here. This is the working algorithm for the merge sorts, but because of time, I didn't get a chance to write the mathematical proof of concept for this algorithm. I'll make a separate video to write a mathematical proof concept for this merge sort. But by comparing the time complexity, which is the asymptotic notation of merge sort and insertion sorts, it is clear that merge sort has the best time complexity. Before I sign out, I would like to share with you the materials I've been studying to prepare for this tutorial. Introductions to Algorithms by Coleman, Insertion, Reversed, and Stein. I'll add a link below in case you want to purchase this book and follow along my tutorials. The last material that I've been using is Cracking the Coding Interview by Gail. I'll add a link below as well. You can purchase this from Amazon and you can follow along this tutorial. In this video, we talked about why you need to study algorithms, some problems that has been solved using algorithms, 3 most important restraints to consider when implementing algorithm, and we picked 2 examples of sorting algorithm, merge sort and insertion sort. We discussed their time complexities, compare both, and we've decided merge sort is the best. If you did enjoy the video, please click the like button and subscribe for more future videos. If you have any questions or concern, please feel free to comment below. Without wasting much time, I will say bye-bye.